This lecture is titled Fundamental Laws Plus, and as the name suggests, we're going to touch upon those fundamental laws. For example, Telegon's theorem, Ohm's law, Kirchhoff's voltage law, Kirchhoff's current law, the laws that you need to understand in order to analyze basic electric circuits. We're going to introduce them from a theoretical point of view, as well as address tons of really great concrete examples where we apply those laws to solve electric circuits, as you would imagine. Now, this lecture represents a little bit of a turning point in this course. Before this, we were largely dealing with introductory material, and perhaps some of that material is not included in a traditional circuits course. But from this point forward, we are going to get into the real nuts and bolts, the meat and potatoes of electric circuit analysis, and largely be dealing with material that would be included in any traditional circuits course. So before we jump into those laws, let's begin by discussing a few other fundamentals, the first one being the difference between alternating and direct current.
Now, what is AC? What is DC? Let's start off by talking about the formal definition, and then we'll work our way back to the ways in which those terms are more commonly used. In its simplest form, a DC current, a direct current, is one whose flow is unidirectional. And so we have two examples here in the green and the blue. We have a constant or a static DC current, as well as here in the yellow, some sort of sawtooth wave type, time varying and oscillating, but yet still DC current. The reason being is it does not cross the x-axis here. On the right-hand side, we have two examples of an AC current, an alternating current, whose direction does reverse. We have the blue, which is kind of a square wave type AC current. And then we have the purple, which is your basic sinusoidal. Now, those are the formal ways in which those terms are defined. How are we going to use them? More times than not, in this course especially, we're going to be talking about DC as being a static signal, sort of like the green. Something that looks like this. More times than not, engineers, as well as in this class, we refer to AC, or when we refer to AC, we're really talking about a sinusoidal waveform. Something similar to what you see in the purple. This is the reason why when, let's say, for example, you take a power class, they'll often talk about AC circuit analysis, but that really means sinusoidal, right? There's not any square waves in a power system. All right, so now we understand, and actually lastly, what about voltages? So AC stands for alternating current, DC stands for direct current. However, we often say AC current and DC current, AC voltage, DC voltage. So those terms kind of have morphed into adjectives. Labeling voltages and currents. Now, this may seem like a sort of trivial topic. It's very important for succeeding in this class, and we'll see very quickly why. Voltages and currents have no preferential direction, okay? Sorry, I meant to use my highlighter there. Have no preferential direction. And so we can define them literally in any way that we want so let's take a look at these two examples. Let's say we have a resistor, or any element, doesn't matter what it is. We want to have some way of referring to the voltage across it. We can refer to the voltage as shown in V1, with the polarity being plus minus, or the voltage V2 with the polarity being minus plus. Both of those are equally correct. The only difference is, we know that V1 is equal to negative V2. So you can define the voltage across that resistor in either of those two ways. And when you solve for V1 or V2 at the end, you'll have to refer back to the figure in order to understand physically what that voltage means. We have a similar situation with currents. We can define the referential direction of current through a resistor or any element as flowing to the right or flowing to the left. Obviously, they have opposite directions, so I1 equals negative I2. And depending on which one you choose, whatever numerical answer you end up with at the end of the problem, you'd have to compare that or use the referential direction in order to understand what that physically means. So the assumed polarity of voltages and direction of currents, they are arbitrary. It doesn't mean that they're unimportant, They still play an important role in using the equations introduced below correctly. So again, the numerical answer that you come up with from an equation, quote unquote an equation, really has no meaning if you don't understand what the polarity or direction of that value is. Because, saying that the voltage across the resistor is 12 volts It doesn't really tell us much if we don't know whether we're referring to V1 or V2. All right, passive sign convention. Now this is a really important topic. It's one that every year I teach this course, I very much encourage students to spend a lot of time making sure to understand this. You know, we always have students that don't, and it always ends up biting them in the rear over and over again because it plays a major role in making mistakes related to reversing the signs and directions of voltages and currents. So let's talk about what it is. It's actually a pretty simple concept. We already know that resistance defines the ratio of the voltage across an element and the current it conducts. We talked about that briefly in the last lecture. We're going to be talking about that more in this one as we dive into Ohm's law. But hopefully you all understand that we know R equals V over I, the ratio of the voltage across and the current through an element. But going back to our previous section here, how do we know what the polarities and the directions are, right? The signs are important here. And that's exactly what the passive sign convention addresses. So how do we know which way is which? Let's take a look here at 3 different cases. We have the first case where the current shown in green is flowing downward and the voltage is plus minus, top being plus, bottom being minus. We have the blue where the current is flowing up and the voltage polarity is top plus, bottom minus. And then we have the third case where the current is flowing down and the voltage polarity is top minus, bottom plus. So these 3 circuits describe conflicting situations. So the equation V equals IR, right, it cannot be correct in all 3 cases. Now really the important thing to note here when we compare cases 1, 2, and 3 is not the direction or the polarities, the absolute direction or polarities, but the relationships between them. You can see here in the first one, our current is flowing from positive to minus to the negative terminal. Here it's flowing from the negative to the positive terminal, and here it's also flowing from the negative to the positive terminal. Even though the current here is flowing down, the current here is flowing up, it's this relative direction that is the most important. So again, all 3 of those equations cannot be the same or cannot be correct because they describe conflicting situations. So we need a way to keep track of our voltage polarities and current directions so we can use Ohm's law properly. What if we simply assume a relationship? Now, this is not just any assumption. It's an assumption we'll see that allows us to use V equals IR without inserting any additional negative signs or negative ones. So the passive sign convention is this assumption, one that we're going to use heavily in this class. It allows us to properly use Ohm's law and many similar equations. And so what it says is that if a current I flows from the positive to the negative terminal of a resistive element, or really any element, then Ohm's law applies as shown here. V equals IR, positive IR. Now, we could define another current here, which I'm going to call I prime. And we could come up with an alternative form of Ohm's law, which would be V equals negative IR. You don't have to use the passive sign convention. You can find alternative ways. However, I would ask the question, do you really want to be coming up with equations like this every time for every step of solving an electric circuit analysis problem? No. And so even for people who have spent a lot of time working on this type of material, one example being myself, I pretty much always stick with the passive sign convention. It really just makes things a lot easier. One less thing to worry about. So the passive sign convention does not require that the values of V or I be positive, right? The directions are referential. However, the value could be negative, indicating the actual flow is in the opposite direction. So that's one thing to remember here, is that these are referential directions. It's sort of like saying which way is up and which way is down. It doesn't mean that because up is up and down is down, you're going in any given direction. It's simply just laying out the rules for our calculations. And so here we can see a system that obeys the passive sign convention, right? We have current flowing from the positive to the negative terminal. However, the current is negative 2 amps, and so the voltage across it is negative 20 volts. Both the current and the voltage end up being negative. And there's nothing wrong with that. That's a perfectly fine way of using the passive sign convention. Both values end up negative, but we don't need to change our reference polarity or direction. So if we thought about this physically, we know that the current is actually flowing in this direction with a intensity or a magnitude of 2 amps. Furthermore, we can violate the passive sign convention and generate correct values, but only if we adapt our equation for this different convention. And so this figure here is similar to the example I already gave. Right. Here we have a current that's flowing from the negative to the positive terminal, and we can still calculate V using Ohm's law. However, we have to make sure to insert this additional -1. So if we have V as negative positive, we have our current flowing downward with an intensity magnitude of 5 amps, and our resistance is 0.5 ohms. We see that V equals -1 times IR equals -2.5 volts. Now we can try doing the same problem except the passive sign convention. So we flipped our sign V, all right, as compared to the left-hand side. Now the current is flowing from the positive to the negative terminal, and I'm going to call this V prime. And so our passive sign convention gives us the solution of positive 2.5 volts, right? Because now V equals positive IR. But these conflict. We have negative 2.5 and positive 2.5, so this didn't work, right? We ended up with two different answers, except, right, it did. Because remember here that the polarity of this V and the polarity of this V over here are opposite. So that means that V equals negative V prime, and as you would expect, negative 2.5 volts equals negative 2.5 volts, and everything works out. So I don't want to throw too much information at you because that can be confusing. I would say the most important takeaway here is this figure, okay? We know that if the current flows from the positive to the negative terminal of some element, it adheres to what we call the passive sign convention. And if that is the case, we can use Ohm's law as defined here. V equals IR. We'll later also see that we can calculate P equals VI, the power being absorbed by that element, and we know that the referential direction is power being extracted from the system, but we're not going to talk about that just yet. This next section is titled Theoretical Analysis, or the equations required for theoretical analysis. Finally, we're going to jump into some of those fundamental laws that we were talking about earlier. So, like I said, below are the most fundamental equations or laws for circuit analysis. We've talked about a few of them before, one of them being Ohm's law, but we're still going to review all of them from scratch as if it's the first time we're introducing them. So we have Ohm's law, right? It says that the voltage across the terminals of a resistive element can be described as a function of the current it conducts. And the form that's shown right here, again, assumes the passive sign convention. So voltage equals current times resistance. Again, we hopefully, it's only been like 2 seconds, remember what the passive sign convention indicates or what that means, but it means that our current, the referential direction of our current is flowing from the positive to the negative terminal of the referential voltage polarity. Next, we have power. So power is defined as the product of the voltage and current again, assuming the passive sign convention. Now, what do we mean assuming the passive sign convention? Because when we talk about power, right, power can flow in two directions, right? This could be power that's pulled from the system. One example being a heating element. Let's say you heat up a radiator, or, well, I guess a radiator is steam, but some sort of electric heating element, right? And it draws power from the system and creates heat. However, you can also have something like a thermocouple, which draws heat or some other form of energy from the system or photovoltaic cell and generates power. So again, we need to know what the direction of the power is here. So P equals VI, if we assume the passive sign convention, means the amount of power being absorbed or taken from the circuit. So P equals VI, we're assuming the passive sign convention. We have, let's say, a voltage 2 volts and a current 1 amp. And so what that's doing is that's drawing 2 watts from the system, out of the system. If we had P equals, so 2 volts times negative 1 amp, that would give us negative 2 watts, which would indicate that 2 watts is being injected into the system. Now, there's several other forms of this equation, right? We have P equals VI, we also have V squared over R, and then we have I squared R, and these are simply just substitutions using Ohm's law, right? So for this one right here, what we did is we substituted in for I, V over R, and for this one here, we substituted in for V with IR. So all three of these, P equals VI, P equals V squared over R, P equals I squared R, all of those, if they obey the passive sign convention, describe the amount of power being drawn from an element, from the system, and being converted to some other form. Next, we have energy. So we've talked about power and energy in that previous lecture. We went into a lot of detail there. Hopefully you remember energy is simply the integral of power with respect to time. And so, sorry this got split up on 2 different pages, but we can simply calculate that as the integral from 0 to t of our power integrated with respect to time. And we have a discrete form here where the amount of power being consumed at a given instant times a delta t would give us the amount of energy being consumed during that time. Now, this would obviously assume that this is a constant value. Okay, so homeworks here, what I'm going to do, previously I had blocked out the homework solutions from the lecture because I wanted students to do them on their own. I feel like that's not a good way to go about this, but they're not intended to be examples. They are intended to be homeworks. So what I'm going to do is I'm going to go over these homework problems pretty briefly. I'm going to post the PDF in the video description. But, I do recommend that you use these as actual homeworks. So perhaps this is a good time to pause the video, take a stab at this, at this problem, and then come back and take a look at the solution. But again, it's up to you how you want to use these. So, homework, our first homework that's embedded in the lecture. Let's solve for the currents I1 and I2 in the circuits below. So we have 3 different cases. 1, 2, 3. So how are we going to do this? Well, let's take a look at the first problem first. Number 1, we know that the voltage with the assumed referential direction right here is 1 volt across it, and it has a resistance of 2 ohms, and the I here obeys the passive sign convention. Okay, so we know that we can use V equals IR, and we could easily substitute in our known values to solve. Let's take a look at the second one. Here we can see this also obeys the passive sign convention, right? The current is flowing from the positive to the negative terminals. So we can use that equation again. Over here, it does not obey the passive sign convention. We have I3 flowing from the negative to the positive terminal of this element. That doesn't mean that it can't be solved. It just means we need to be a little bit careful with how we solve it. So the first step that I recommend here is for you to check the passive sign convention, and like we showed a second ago, the first 2, the answer is yes, and the third one, the answer is no. Now, let's go ahead and in our second step, let's solve for I1 and I2, the first 2 examples, because they already follow the passive sign convention, and so hopefully we're pretty familiar with how to solve those. All we have to do for these is just use a rearranged version of V equals IR with everything being positive. Or we don't know if the numerical value is positive, but the variables are not, they don't have a negative coefficient. And so I equals V over R, I equals V over R. We end up with 0.5 amps and negative 0.5 amps. Now these answers match when we consider the directions of the currents. What does that mean? If you look up here at the problem, the way it was posed, what you can see here is that these two examples really describe the same situation. V1 is 1 volt plus minus. This one, V2, has the polarity reversed, but it also has the sign reversed. So it's really describing the same situation. Everything is flipped. And so we would expect to get the exact same numerical answer, except with the sign flipped. And that's what we end up with here, is a positive 0.5 and a negative 0.5 amps. So that's good. All right, now let's tackle the third. So what can we do? Now there's a lot of different ways to deal with something like this. You can simply adapt the equation. I would say it's generally easier just to define another referential voltage or referential current, solve that does obey the passive sign convention, solve for that, and then flip it as needed. So that's what we did here. We defined this new current called I3R reversed, and we know these directions oppose one another. So I3 equals negative I3R. So we can solve for this and then come up with that. And like I said before, I3R does obey the passive sign convention when compared to this V3 over here. All right, so what we're going to do is we are going to solve for I3R. It's V3 over R, same passive sign convention based equation. And we end up with negative 0.5 amps. And it's pretty easy to convert one to the other. We simply multiply by negative 1, and that gives us 0.5 amps positive. And you can see that this answer is consistent with the other two that we got up above, where the direction of I3 matches that of I1. I1 gives us positive 0.5 amps, and I3 gives us positive 0.5 amps. So if you don't fully understand why these three cases are similar to one another, or why they should be yielding consistent answers, I think the best way to peel back the layers of that onion is to try to put all three of these in terms of the same variables with the same directions, adjusting the values and such. And what you'll see is you end up with the exact same circuit 3 different times. So it makes sense that we end up with consistent values. All right, impedance. So far we've talked about Ohm's law, we've talked about passive sign convention, and we've been discussing it simply in terms of resistance. So part of those notes above, they're incomplete. We said that Ohm's law states V equals IR, but that's really not the whole picture. The more complete form of that equation is V equals IZ, or voltage equals current times impedance. Again, the sign is based on us assuming passive sign convention. These little arrow hats up above, my variables, they indicate, at least in my notes, that this is intended to be a vector or some sort of oscillating value, although impedance is not oscillating. But I don't want to spend too much time talking about this. We do have several lectures that are going to focus on AC circuits, steady state sinusoidal analysis. So this is really neither the time nor the place to dive too much into that. But I do want to talk about the concept of impedance and what that means. So for AC circuits, and we're talking predominantly about SSS, steady state sinusoidal circuits, the relationship between the sinusoidal voltage and current is referred to as impedance. So we have another version of Ohm's law, Z equals V over I. Okay, again, it's still the ratio of voltage to current, except now we have a complex value, R plus JX. Hopefully, you've had a math class that discusses complex numbers. We're going to talk about that a little bit in the steady state sinusoidal section, but we're not going to go into too much of the math theory. But anyway, I equals the square root of 1. We generally don't use I because I represents current. We use J. So when we say R plus JX, we have a real component and we have an imaginary component. The real component is referred to as resistance. And for DC circuits, we don't have any, the numbers are all real. They're not complex. And so impedance is essentially equal to resistance for our DC circuit. Now, for an AC circuit, that's not the case, and we end up with R plus JX. The imaginary component of the impedance is called reactance. Now, the inverse of impedance is called the admittance. So Y is equal to 1 over Z. And that is similarly described in a complex form where the real portion is called conductance and the imaginary portion is called susceptance. You will hear the term conductance utilized in DC circuits. Now, R equals 1 over G. Resistance equals 1 over conductance for DC circuits because our imaginary components don't exist. But this only applies when we don't have any imaginary components. I would suggest that you memorize the names impedance, resistance, reactance, admittance, conductance, susceptance. Those are terms that are really important to understand as someone working in electrical engineering or a corollary area. So, for DC circuits, this is what I just said. For DC circuits, the imaginary components of Z and Y have no effect, and so we end up with V equals IR as opposed to V equals IZ. Okay, next is Telegon's theorem. So, Telegon's theorem tells us that the total power injected into and absorbed from a circuit must equal 0. And as you would expect, this is a form of conservation of energy. So let's take a look at this example here. We have a circuit. It has 4 different elements. We have A, B, C, and D. And we can see that there's a constant current flowing through the entire loop of 2 amps. And we know what the voltage is across each one of these elements: VA, VB, VC, and VD. So let's quickly check to see if this circuit satisfies conservation of energy, satisfies Telegon's theorem. If we want to calculate the amount of power being absorbed by each one of those elements, we need to use P equals VI. However, this only works consistently calculating absorbed power if the passive sign convention applies. So let's take a look here. Current flowing from positive to negative, current flowing from positive to negative, current flowing from positive to negative, current flowing from positive to negative. All right, great. So the passive sign convention is supported by all of those elements, so we can just go ahead and calculate P equals VI without any negatives. And that's what we've done over here. So PA is negative 6 times 2 amps, and that gives us negative 12 watts. PB is positive 1 volt times 2 amps, and that gives us positive 2 watts. We have PC, which is 3 volts, positive 3 volts times 2 amps. Again, that same 2 amps, which gives us positive 6 watts. And then PD, we have positive 2 volts, again, positive 2 amps. And the answer is positive 4. And we could add all these together. 6 plus 4 is 10. 10 plus 2 is 12. So we have positive 12 minus 12, and that gives us a sum of 0. So that is an example of a consistent circuit, or a circuit that obeys conservation of energy and obeys Telegon's theorem. Now, this may not seem very useful in and of itself on its own, but it does help us derive several other laws. One example being Kirchhoff's voltage law. So let's move on to that. Kirchhoff's voltage law states that the voltages in any given loop must sum to 0. And the funny thing about this is there's lots of different ways to describe loops in a circuit. So if we take a look at this circuit right here, how many loops do we see? All right, we obviously see the outer loop. We have an inner loop here, and we have an inner loop here. Something like this infinity symbol, that would not be considered a loop, right? A loop there's two rules essentially. It has to return to the spot that it started, okay? And it can't pass through any branch or any node more than one time. Okay, so the infinity symbol breaks that because, right, it passes through that branch C 2 times. All right, now let's assume we have these given voltages over here. And, right, we should be able to apply KVL. Let's quickly take a look at 1 or 2. So VA, VB, and VC. Let's sum those voltages together. So VA is 10, VB is 3, VC is 7. That equals 20. It's not equal to 0. All right, what's the reason for that? We're going to see in a second that, like how we really focused on polarity earlier, it's really important to focus on polarity here as well, right? Because as you can imagine, it makes a difference whether VC is positive or whether the polarity is positive, negative, or negative, positive. And we haven't taken into account polarity, and that's the reason why we ended up with that funky answer over there. So let's talk about the proper way to do this. So this is the proper way to analyze that loop ABC. VA minus VB minus VC. But that brings up the question, why is VA positive but VB is negative and VC is negative? And the reason for that is because we chose VA as our reference polarity. What does that mean? Now, as we go in a loop, we see that all of the polarities can quote unquote match one another, or we can have differing polarities. And the way that we define a polarity as matching is if a current flowing through that loop always sees the same order of plus and minus. So let's say, for example, if I wanted to make all these polarities match, and let's assume that my current is flowing like this. Actually, I'm going to reverse it so it's plus minus. Let's say our current is flowing like this. For VA, it sees plus, then minus. To make the polarity of VC match, it would have to see plus, then minus. And VB would be plus, then minus. However, that's not the case. And so what we can see here is that if this polarity is assumed to be positive, then these two polarities are assumed to be negative. Or it's really the term positive and negative is not appropriate here. We can just talk about like our referential polarity and the opposite of that. When we do this calculation for KVL, we need to pick one polarity as assumed to be positive, that's our reference polarity, and then the other ones we say are the opposite or negative. It doesn't really matter. We could very easily refer to our referential direction as negative and the other ones would be positive. But the important thing is that the signs have to oppose one another. So that is why we end up with the equation positive VA minus VB minus VC. And now we can plug in those numerical values, positive 10, positive 3, positive 7, and we end up with a 0. Let's try the same thing for this loop right here. And what I'm going to do is I'm going to draw my current obeying the passive sign convention for VC. So we have to pick one polarity as the positive one or the referential one. I'm going to call VC the referential positive. So our current flows positive, then negative. Over here, it flows negative, then positive. over here, it flows negative then positive. So again, if we want to apply KVL, it's VC minus VD minus VE. And that is what we see here. Again, we plug in our values and we end up with a 0. We can do the same thing for the larger loop. The larger loop, right, I'm going to assume that the current, and let me just say here that I'm not really calculating this current. I'm just using it as a tool to help me differentiate the polarities. So I'm going to assume this is positive. So it flows positive, negative. Over here it's negative, positive, negative, positive, negative, positive. So VA minus VB minus VD minus VE. Here we use a similar setup, 10 minus a positive 3 minus a positive 1 minus a positive 6, and that gives us 0. Now, we can also use KVL to calculate the voltage between 2 points. It doesn't necessarily have to be a loop, although in reality we are still making a loop. Because let's say we have points A, B, C, and D, and we want to know the voltage VAD. Now, we haven't explicitly talked about the double subscript notation, but that is one we're going to use heavily in this class. When I say VAD, that essentially means VA minus VD, or the voltage between those 2 points. Okay, so going back to this now. What is VAD? So VAD is the sum of the voltages in between those 2 points. Now, we said this isn't a loop, but it kind of is a loop. You can think about it as a loop. So let's imagine that we have a current flowing like this. Then we can use our same version of KVL from above. So this is a positive polarity, this is negative, this is negative. Sorry, no, this is positive, and this is negative. Okay, again, assuming that this is the positive referential direction. So we have VAD minus V3 plus V2 minus V1 equals 0. Another way to write that is VAD equals V1 minus V2 plus V3, which is essentially what you get if you simply just added up the voltages here with the assumption that we're looking at the voltage differential between A and D. And so here we can see this version of the equation and this version of the equation match. So KVL can be used to both perform calculations, right? This knowledge that all of the voltages in a loop must sum to 0 is very useful for calculating unknown values. But it can also be applied in a more general form to calculate the voltage differential between 2 points as the sum of other intermediate voltages. The voltage difference between VA and VD is going to be plus V1 because the polarity of V1 matches VAD, and so on. So it's always important to clearly define the reference polarity. Otherwise, we don't know which voltages are positive or negative. We've already talked about that pretty robustly. We've talked about it a lot in that previous little section. Now, we haven't really talked about a general mathematical form of KVL. That's shown right here. Essentially, the sum of all the voltages in a loop equals 0 when you take into account the positive or negative 1 that is applied. It's applied positive if the polarity matches our reference and negative if it opposes. Again, though, just really quick, you can choose the reference direction however you want. Let's say that we did loop ABC again, but this time we chose VB as positive. The polarity of VC matched VB, and now VA is opposite. So what we end up with is negative 10 plus 3 plus 7, which still equals 0. I think this is one of the things in this class that takes some getting used to, is this idea of referential directions. Referential polarities, referential directions of current, and how we essentially have a lot of freedom to assign those however we want. And that sometimes can make things more difficult, which is why, not to sound like a broken record, I generally suggest we rely heavily on things like the passive sign convention to take away some of that choice and kind of make things easier. All right, let's check out this problem here. We want to solve for the unknown voltage V2 and then use Talagin's theorem to solve for I3. So what we have is a pretty basic circuit. It's got 4 elements, essentially in 2 mini loops here. We know V1, V3, V4, I1, I2. We don't know V2, and we don't know I3. So we're going to use a combination of KVL and Talagin's theorem in order to solve for the unknown values. So the first step is going to be to use the loop 1, 2, 3, this one here, okay, to solve for V2 using KVL. Since we know 2 of the 3 values, we can easily solve for the third. So as you can see here, we have 2 different options to apply KVL. We can use this loop, or we can use the bigger loop. Either one is fine because both will include V2 and both will have all the other values being known. Now, the only option that wouldn't work is, hopefully it's obvious, using this loop would not work because it doesn't include V2. All right, so now let's go ahead and figure out what the polarities are supposed to be. I'm going to go ahead and assume that our current is flowing in this direction. And remember, this is not really a current. I'm just using this to decide or to determine what the referential polarity is. So I'm going to imagine that this current exists, and it obeys the passive sign convention with regard to the first voltage. So this is going to be referential positive. Then we keep going. Okay, keep going. We reach V3. We see that flows negative to positive. So that would have the opposite sign. And same thing with V2, opposite sign. So we end up with V1 minus V2 minus V3 equals 0. That's how we should apply KVL. And you can see we have very similar, well, the same equation here. So V1 minus V2 minus V3 equals 0. We can solve for V2, which is V1 minus V3. And that gives us negative 5 minus 2 equals negative 7. So that's our value for V2. And if we plug in all the values, hopefully we should see that we end up with a net 0. Let's go ahead and plug them in. So V1 is negative 5. Okay. V2 is negative 7. And V3 is positive 2. So if we're flowing in this direction here, okay, what we end up with is a voltage of negative 5, then another voltage that gets reduced by 2, so that'll become negative 7, and then because we're flowing in the opposite direction, this negative 7 will actually boost the voltage by 7, giving us a net 0. I'm not sure if that will make sense to everybody, but just a quick check of what we did. All right, now let's go ahead and define Talagin's theorem for that same circuit and see if we can solve for the unknown current. So what I did was I set up Talagin's theorem right here, which says P1 plus P2 plus P3 plus P4 equals 0. Now remember, for Talagin's theorem, it's not just a single loop. It's every single element in that circuit. So we have to include all 4. Now, if I can clean this up a little bit, what we see is that sorry, I'm just trying to clean this up. So we see that I3 and V4, these two, they satisfy the passive sign convention. So we know that P4 should be equal to I3 V4. That's good. I2 and V3, those also satisfy the passive sign convention. So we can imagine P3 will be equal to I2 V3. Okay, good. I1 and V2 satisfy the passive sign convention. So P2 will be equal to I1 V2. Now the only outlier here is V1, which does not satisfy the passive sign convention. Now we could, flip the voltage and, account for that, but really we could just take a shortcut here and say that P1 will be equal to negative I1 V1. Okay, so we're going to take this, and this, and plug it in down here. And you can see we end up with 4 different values. We end up with negative V1 I1. Remember, that's the only one that doesn't satisfy the passive sign convention. V2 I1, V3 I2, V4 I3. The only unknown value is I3. And so as you can see, we have a pretty clear algebraic equation, and we can solve for I3. So we move these terms over to the other side of the equation. We divide by the V4, and we end up with that expression below. Then we plug in some of the values, here, 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 and here, and we end up with a value of negative 1 amp. Now, let's check to see if that value makes sense, and this is going to give us a preview of KCL, Kirchhoff's current law. Let's take a look here real quick. I want to focus on this node. All right. We already know that I3 is, I3 we just solved was negative 1 amp. So I'm going to say that's the same as 1 amp heading into the node, right? Because I3 is flowing the other direction. We know that I2 is 2 amps. And we know that I1 is 1 amp. So think about this in terms of conservation of energy, conservation of matter, whatever you want to say. Does this make sense? Right? We have, imagine this is like a factory, right? We have 1 amp worth of material going in, another amp worth of material going in, and 2 amps coming out. That makes sense, right? We have 2 amps going in, 1 plus 1, and we have 2 amps going out. And that's essentially the basis for KCL, which can be derived from Telegon's theorem or can be derived in other ways. But this example here just simply demonstrates how we can use both KVL and Telegon's theorem to perform some pretty simple circuit analysis, right? We solve for 2 unknown values. So we've talked about Kirchhoff's voltage law, we've talked about Telegon's theorem, we've talked about Ohm's law, a couple of different useful tools. Now let's move on to Kirchhoff's current law. So Kirchhoff's current law states that all the currents flowing into a node or any subcircuit, and this is one thing that students often forget, is it doesn't just apply to a node, it can apply to any, there's some rules, but any self-contained subcircuit. So the sum of those currents must equal 0. It can also be described as the requirement that the sum of all currents flowing into a node equal the sum of all of those flowing out. So I have two different versions drawn here. This one simply says we have 3 currents flowing into the node and the sum of those 3 currents must equal 0. Or you can look at it as 2 flowing in, 1 or 2 flowing out. The sum of those flowing in must equal the sum of those flowing out. I think for most students, this is a pretty intuitive rule. I mean, if you just imagine something as mundane as delivering apples, right? If you bring in 5 apples on this road and you bring in 2 apples on this road, you have to have 7 apples flowing out. So yeah, hopefully that's pretty intuitive. So let's take a look at another mini homework problem here. We want to write KCL for every node in the circuit below. All right, so here's our circuit. Now, I think one thing we haven't gotten too much into is proper labeling of nodes. And that's something we're going to talk about a little bit later. So for right now, let's just go ahead and assume that I'm telling you what the nodes are in this circuit. We have one large node up along the top here, which spans several different junction points. That's N1. We have N2, we have N3, we have N4, and then we have node 5, which spans all the way along the bottom here. Now the first step, and we're going to see this show up in a lot of different problems, is we want to make sure we're labeling all the nodes, the voltages, and the currents. I prefer to label them, using the passive sign convention. That's not a hard, steadfast rule, but it's my suggestion. And so now we can see here, well, I didn't really label the voltages because we're not dealing with those since this is predominantly a KCL problem, but I did label all the currents, right? We have I1, I2, I3. Anyway, this is a pretty straightforward problem, I think. I'm not really going to even review every single part of the solution. If we look at the first node, we see that the sum of all three of those currents must equal 0. And so we have positive I1 because that's flowing into the node, negative I2 because that's flowing out, and negative I3 because that's also flowing out. We can take a look at node number 2, which is right here. Now, one check you can use when applying KCL is to look at the number of branches or the number of currents that are connected to the node, and that should match up, assuming you're not doing some sort of simplification, that should match up with the number of terms, additive terms that you have. So here we have 3 different branches that are adjacent to node 2, and there's 3 currents. We have I3, we have I5, and we have I8. So right off the bat, I know this is going to be plus or minus I3, plus or minus I5, plus or minus I8 equals 0. And then all we have to do is figure out what the signs are. Now, there's similarly to how we treated KVL, we do need to assume a referential direction. Normally, I'll use flowing into the node as the referential positive direction, but you don't have to. So if we assume that currents flowing into the node are positive, that will give us positive I3, negative I5, and negative I8. And you can see that's pretty similar to what we have written right here. So I'll let you take a look at the rest of these on your own. This is a kind of complex looking circuit, but we're applying a pretty simple analysis to it, which is just simply declaring KCL. Now, moving on, and we're not going to do that here, what would normally be the next step in a problem like this? Okay, the next step in a problem like this would normally be to substitute for our currents using Ohm's law or something similar, and that would allow us to move forward and potentially solve for voltages or whatever values that we're concerned with. So really nice, concise, short problem. All right, let's take a look at another example here. We want to solve for the current I3 below. Now, we're getting into a slightly more complicated looking circuit. We have, 1, 2, 3, 4, 5, 6 resistors and a voltage source. And we want to solve for I3. Now, there's a hard way of doing this. You could go and solve for all the node voltages and go, forth in that way. However, remember we said that KCL applies to any node or sub-circuit. So if I take everything that's highlighted in yellow and circled in blue, and I consider that to be a single node, right, or a single object, we can simply just apply KCL to this larger area as if it were a node. And that is what is shown right here. We have 2 currents flowing in, I1 and I2. We have 2 currents flowing out, I3 and I4. We know I1, we know I2, we know I4, we don't know I3. And then the rest of it is pretty straightforward, right? We substitute in the values that we know. I'll do some of the math here. So we have 2 minus 3 minus 6. So that will give us 2 minus 9, which is our negative 7, as we see right there. So, that's another really short and concise KCL example that we can use. All right. So now let's shift gears just a little bit and start talking about some terms, because there are definitely especially when we go back to that second to last example. We have not really talked about the difference between a junction and a node and how to properly label nodes, so we were getting perhaps a little bit ahead of ourselves. So let's dial it back for a second and talk about some of these important terms. Okay, so a junction is any point in a circuit where two or more connections meet. So if we go back up here to this example, what we could see is that this is a junction, this is a junction, this is a junction, 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 junction. Okay, there are more junctions than there are nodes, or what we're going to call electrically independent nodes in this circuit. So anytime we want to refer to the most basic intersection, we'll call that a junction, or we could use the word intersection as well. A short is a connection between two junctions for which the voltage between them is zero. Normally, if we have a junction and a line between it, we consider that to be a short. We could also represent that as a resistance where R equals 0. Now there's other examples for a DC circuit. This would also be a short, but I'm not going to get into those details. Just being familiar with the term is good enough at this point. So we call that a short. I guess you could also call it a shorted branch, although we reserve the term branch for non-shorts. So a non-short branch, or what we're just going to call a branch, is a connection between two junctions for which the voltage differential is not equal to 0. So if we have something like this, where R is equal to 10, and there is some current flowing through it, that would be a non-shorted branch. It would be a branch. Also something like this, that would also be a branch. So essentially, the rule of thumb here is that you have to consider anytime there's a link between two junctions, we need to determine and assign them as either being a short or being a branch, a non-shorted branch. Now, this is the really important one. An electrically independent node. A junction or a point. So an electrically independent node is a junction or a point that is not shorted to any others. Nodes are separated by branches. So if we go back up to our example here, and let me draw a little bit of a divider. All right, so up here we have the shorts, down here we have the non-shorts. Okay, so we have two junctions separated by a short. Because they are connected in that way, these are not electrically independent from one another. In fact, as you saw in the figure above, I could combine the two of these together and potentially call them a single node. Same thing for this. However, down here, we have a junction, and it's separated by a branch where we assume the voltage is non-zero across that. And so I can call this node 1 and I can call this node 2. Now, all things being equal, we don't know what the rest of the circuit looks like. Same thing here. I can call this node 3. I can call this node 4. So understanding the relationship between junctions, shorts, branches, and electrically independent nodes is important. And I want to spend 1 second also talking about what electrically independent means. So the reason why these two are not separate nodes is because they're not electrically independent from one another. And why are they not electrically independent from one another? Because they're shorted together, which means whatever the voltage is here will be the same as the voltage over here. So if you think about it from a mathematical standpoint, it doesn't make sense to calculate both of these voltages, right? They're the same value, which means we should just consider them as a single element, which is why they're not electrically independent from one another and why they don't constitute two separate electrically independent nodes. Now, I feel like this concept is probably best demonstrated through examples, and when we get more into nodal and mesh analysis, we'll have more than enough chances to do that. So take that at face value for right now, and we'll slowly get better at this. Here we have an example, and let's take a look at what we have. So first, we have how many junctions? 1, 2, 3, 4, 5, 6. Okay? Fair enough. Good. We know that. Next, let's go through and try to count the number of branches that we have. We have, and they're numbered 1. Sorry, my highlighter didn't work. 1, 2, 3, 4, 5. Okay, great. How many shorts do we see? There's a short here and there's a short here. Okay, so now that we understand we have 6 junctions, and we understand we have 5 branches, and we understand that we have 2 shorts, how do we determine what the electrically independent nodes are and how many of them there are? So my suggestion is to do it in this way. Let's start with a single junction. Okay, we'll start here in the top left-hand corner. Then what we do is we look at everything that it's connected to, and we look for shorts. Now, if we go downward, there's no short connection here, so we don't have to worry about that. However, if we go to the right, we see that these two are shorted together. In that case, what I'm going to do is I'm going to call the two of these a single node. All right, now I'm going to move over to this node. Let's do the same thing. Let's look, or this junction. Let's look to the right. Let's look down. No shorted connections. So that means we don't have to extend this node any further. All right, so we have now our first node. Now let's jump over here. Do the same thing. Look left, look down. Are there any shorts? There is. There's a short to the junction below it. All right, so what I'm going to do is I'm going to declare these two to be the same node, which I label node number 2. Then I jump down to this one. And no shorts. Okay, so we don't have to worry about extending that node. Now we jump over here. This is not shorted to anything else. All right, so it's going to be its own node. And then this one, lastly, it's not shorted to anything else, so it will be its own node. And so you can see, by going around the circuit in that way, we've determined that there are 4 electrically independent nodes out of the 6 junctions. Now let's talk about loops. So nodes are going to be very important when we get to discussion of nodal analysis, as the name may suggest. Loops, or the understanding of how to define proper loops, is going to be very important for, well, multiple things, but predominantly when we dive into mesh analysis. So a loop is any closed path that does not traverse any branch, sorry, the word branch should be in there, any branch or node twice. So as you can see here from the circuit we have drawn, there's 3 different loops that can be drawn. 1, 2, and 3. One traverses the inner left loop, one traverses the inner right loop, and then one goes around the outside. So a loop that does this, right, that would not be appropriate because it would traverse multiple, well, the branch in the middle 2 times and multiple nodes 2 times. So I don't know if I've talked about this before, but the ability to properly quantify the number of electrically independent nodes in a circuit, as well as the number of consistent loops in a circuit, is important later on because it helps us understand how many unknowns we have, how many variables for which we're trying to solve. For example, if we look at this circuit right here, we see that because there are 4 electrically independent nodes, we are going to be solving for V1, V2, V3, and V4. Right? If you thought that these were 2 different nodes, then you might be trying to solve for an additional value V5, which is the same as V4 and could lead to having potentially, in mathematical terms, an underconstrained problem. So it's very important to be able to quantify the number of electrically independent nodes as well as the number of electrically independent loops. All right, now let's move on to circuit labeling. This is a very practical task, a very practical operation, but it's one that's extremely important. Dealing with circuits, it's not very intuitive in a visual sense, which I think is one of the reasons why electrical engineering is, always had a little bit of a less popularity as compared to mechanical engineering, because, with mechanical engineering, you can kind of see what's going on, and with electrical, you can't. So it's very important, that we do things in a mathematical way, and it's also very important that we label things properly, because we want to understand how to reference every single value in the circuit. We want to use as few labels as possible, and we want to make sure that there's no confusion or overlapping labels, right? Something that refers to two different things. Generally, in circuit textbooks and the way that I suggest, we begin by labeling the nodes. So you can see here, we have 6 junctions and 5 electrically independent nodes, A, B, C, D, and E. Right, so that's normally the first part. Oh, sorry, there's only 4 electrically independent nodes. These 2 are the same, and these 2 are the same. So A, B, C, and D. Okay. Now, the nice thing about labeling in this way is now we can use the double subscript notation to refer to lots of values. So let's say we're concerned with the voltage between here and here. We can refer to that as VAB, which would be equal to negative VBA. The only difference is going to be the placement of the positive and the negative terminals. Okay, VAB, we have an assumed polarity of plus minus, whereas for VBA, we would have the assumed polarity of minus plus. Same thing for VBC. We could also assign a VCB. We can talk about VCC, which is not the same as, we often use VCC to mean supply, but here it's just the voltage between node C and itself, which will always be equal to 0. And then we have node voltage DC, so on and so on. Right? We can flip the polarity and the subscripts, and they're consistent, and they would be satisfied by the equation over on the right-hand side. Okay, we can do something similar with currents, okay, where we have IAB flowing in that direction. That would be the opposite of what we would call IBA, which would be flowing in the other direction. We have IBC, ICD, IDC. I mean, I could go through and show the difference between each one explicitly, but I think that for most of you, you will kind of understand what it is that we're trying to say here. So we know that we can choose the polarities and directions such that they obey the passive sign convention. So that's nice. Since we are defining what label is used to refer to the voltage across an element, and we are defining what label and direction is used to define the current through an object or an element, we can choose to obey the passive sign convention if we want to. Now remember, one more thing I want to say is there is no guarantee that VAD is going to be greater than 0, right? VAD could very well be less than 0, which means that, in physical terms, the polarity is actually opposite. But we don't need to make that change. Again, this is just a referential polarity or a referential direction, which we're using to help define the numerical answers that we get. So I just don't want anyone to make that assumption. Now, the one caveat here is, if you have, let's say, parallel branches like that, in that case, IBD would, in my mind, refer to the total current through both of the branches. So when you have parallel branches like that, you may need to define, IBD and IBD prime or something along those lines in order to not have redundant, definitions. We can label resistances in a very similar manner using the double subscript notation. Resistance is not directional, so RCD is the same as RDC. We don't have to worry about that. And now we can move from double subscript to what we call the single subscript notation. if we make one node in our circuit the reference voltage, then we can use single subscript notation. Now, let's be careful. There's a difference between the reference direction and the reference voltage. The reference voltage is similar to what we often call the ground or the neutral. So what we're saying here is that if we declare this node as the neutral, as our reference voltage, that is what we assume to be 0 volts. Now, in the end, there is no actual 0 volts, right? Voltage is a differential measurement. It's always measured in reference to something else, which is different from current, right? There is an absolute 0 current, right? We can look at a cross-sectional area of a conductor and tell if there's any charges moving. But with voltage, that sort of absolute measurement doesn't exist. So what we do is we can say, okay, we're assuming that the voltage at node N is equal to 0 for the purposes of this circuit. And then, now what we can do is refer to the voltages at the nodes using just a single subscript. But that's the same as saying VAN, VBN, VCN. So when we say VA, that's VA minus VN. VB is VB minus VN, and so on. So that is exemplified by the math over here. So let's start off with our double subscript notation, VAB. How can we break that down into two different pieces? That is the same as saying VAN minus VBN, the voltage between A and N, the voltage between B and N. Same definition. Now we can say VAN, we can split that up into two pieces, VA minus VN. All right, and you can see here that the VNs cancel out, which then leaves us, after some substitution, with VA minus VB. Perhaps this math is not super useful, but it does demonstrate how we can relate those subscripts to one another, and that the relationships we already know to be true, they hold if we manipulate the subscripts properly. All right, I think we have one more problem to take a look at. So we want to label all the nodes, voltages, currents, and resistances for the circuit below. Label the voltages using both single and double subscript notation. And we're going to assume that node N is the reference node. We want to adhere to the passive sign convention if possible. All right, so let's take a look at what we have here. This is our basic circuit. We've already labeled the nodes. Well, actually, no. They're labeled as junctions. The nodes are not labeled yet because we have 6 junctions and we have A, B, C, D, E, N. Okay, but we can already see, hopefully, that these two are the same node. They are not electrically independent from one another. And these two are also the same node. Okay, and so what we end up with as we go from left to right is we end up with now only 1, 2, 3, 4 electrically independent nodes, which we are going to call A, C, N, and D. So we no longer have a node B, but that's fine. No big deal. Now, what we can do is we can label our voltages using the double subscript notation VAD, VAC, VCN, VDN with the appropriate, I don't want to write on top of everything because it's actually clear the way it's already printed on the screen. All right. So we've labeled all of our voltages using the double subscript notation. Now let's do the same thing for the currents. Now, one quick thing here, right? There's no preference. We could have easily labeled this VCA. Normally we don't do both, right? Because it's redundant and it clutters our diagram. So we know that we can always refer to it as VCA and simply just flip the polarity. All right, now let's take a look at labeling the currents. Again, not necessarily very difficult here. This is going to be VAC because it's flowing from node A to node C. We could call this INC. It's flowing from the neutral to node C. DN, AD, I think Hopefully this is pretty self-explanatory. Now, let's go from double to single subscript. And now essentially all we have to do is refer to a voltage here as VAN, which we can just simply call VA. So now we understand the voltage between here and here. Sorry, not that one. The voltage between here and here, the voltage between here and here, right? There are 3 independently defined voltages in addition to the neutral. That makes sense because we have 1, 2, 3, 4 electrically independent nodes. One of them is our neutral, which leaves 3 values, VA, VC, and VD, for which we need to solve. Vn, we already assumed is equal to 0 because it's our reference voltage for the rest of the circuit. So, I don't think this is necessarily a difficult problem, but it is one that demonstrates good labeling practices. Now, I didn't necessarily touch upon the fact that we followed the passive sign convention, but we did. So we can see IAC, VAC, IDN, VDN, IAD, VAD. So the passive sign convention would apply for all of those. And I know I missed a couple. Like in here, I didn't label IAN. I don't know why I wrote that below it, sorry. IAN, but I think you could fill in those blanks yourself. As we get into more complex problems, I'm going to hope that you can be very meticulous with this first step. It really is a make or break when it comes to solving these types of problems, being able to properly label the nodes. All right, one more homework or example, depending on how you look at it. Let's go through it pretty quickly because we've done a number so far. Calculate the current IL flowing through the load as well as the power absorbed by that load. Okay, so unfortunately we have another case where our circuit's kind of split on 2 pieces, but you can see right the circuit continues. Actually, unfortunately, it's showing things twice. So I'll do that. All right, not the best representation of the circuit, but it works. Okay, so we have a current IS, we have a current IL, we have a node 1, we have a node 2, and we have a voltage source in parallel with a resistive load. So we start off by labeling all the nodes, branches, voltages, and currents. So you can see here we have 2 electrically independent nodes. We have 2 branches, this one and this one. And then the voltages and the currents we can simply, they're already labeled. And we didn't use the double subscript notation, but that's fine. You don't have to. It just makes things easier sometimes. Now, do all of our labels obey the passive sign convention? They do, right? Because IS flows from the positive to negative terminal of VS, and IL flows from the positive to the negative terminal of IL flows from the positive to the negative terminal of VL. So that's good. Now, let's write out the relevant equations we know. And this is just barely dipping our toe into more advanced problems, because this is a strategy that we're going to use a lot. And, honestly, circuit analysis is predominantly a linear algebra course, an application of, algebra and linear algebra. All we do is use the physics behind circuits in order to formulate the equations. And then more times than not, the bulk of the effort and the work, and where more mistakes happen, is in the algebra part, in the linear, either traditional algebra or if we're using matrices, the application of linear algebra. All right, so let's take a look at what we have. We know that, I'm trying to get both on the screen at the same time. We know that VL is equal to IL times RL. And that makes sense because we obey the passive sign convention. And we can also say that IL is equal to VL over RL, 12 volts over 3,000 ohms. And that gives us 4 milliamps. Now you may be asking, how do we know what VL is? We're never told what VL is. And this leads us into our first discussion of parallel and series connections, right? If we have a source and then we have something that shares the same two end nodes, whatever the voltage here is will have the same voltage here, right? Because they share the same two end nodes. We could call this VAB, and both of these would be VAB. So this is probably skipping ahead a little bit, but we're really applying VS in that spot. So we end up with 4 milliamps. So we have 4 milliamps flowing in that direction. We can use then KCL to solve for IS. We're applying KCL at this node right here. We know that IS plus IL equals 0. The sum of all the currents entering or the sum of all currents leaving a node should be equal to 0. And so when we apply that, we see that IS is negative 4 milliamps. That sort of makes sense. We expect to have 4 milliamps flowing in that direction in order to have 4 milliamps flowing in that direction. In order for this to be 4 milliamps, IS needs to be negative 4. So, for these earlier problems, the nice thing is generally, you can use sort of practical logic in order to verify. Then we use KVL. Although this is really kind of redundant because we already made the assumption above that VS was equal to VL, which is what KVL gives us. And then we calculate power. Now, again, remember, this would be power absorbed because we're obeying the passive sign convention. So PL equals VL times IL, 12 volts times 4 milliamps, which gives us 48 milliwatts. That's going to be absorbed by that resistor. Now, in practical terms, where does that energy go? A resistor would heat up, and that would be translated to heat. I'm not going to go through this last step here, which asks you to verify our answer using Telegon's theorem. I'll leave that up to all of you to try. So that marks the end of this lecture. I think it's a really good one. It's probably one of the first ones that will really apply to, let's say, a quiz or an exam that you have in a traditional circuits class. I know that my version of this class has a lot of lead up, talking about physics and, electrical engineering in general, some things that are not traditionally included in a circuits course. But I figured since this may be the first look at electrical engineering or electrical engineering work that many of you have, it kind of makes sense to provide a little bit of a better introduction. So, that's pretty much how the rest of these modules are going to go. The rest of these lectures are going to go. From this point forward, we're going to dive into a much more, what I would say, traditional approach to circuits, like what many of you will see probably at your own institutions. We're going to move on to more complex circuit topologies. We're going to discuss how to use the combination of KVL, KCL, Ohm's law, Telegon's theorem, not so much, but a little bit, and how to combine those laws together to solve increasingly complex circuits. We'll talk more about series and parallel connections. We'll obviously have to talk about different types of sources. We really haven't talked about sources that much. We've sort of assumed what a voltage source does and how it works, but we haven't talked about it specifically. And, slowly just using those building blocks, putting them together in order to solve increasingly complex circuits. And generally, that means solving for the voltages at the nodes, although not always. And when we move into nodal and mesh analysis, we're going to look at more methodical ways to do that and then branch out from there. So I hope this was interesting for all of you. I hope it at least is a good supplement to what many of you may be seeing at your own institutions. And I hope that you'll keep checking out these lectures because the next one will dive into more complex circuit topologies and how to solve them using these methods.